All right. So when you think and talk about innovation, you might think about new idea, how it spreads around, right? Or maybe new technology, how it's going to get adopted. You can think about the way, for example, how online downloading replaced, CDs and DVDs, how those in turn back in the days replaced tapes, and how tapes back in the days replaced vinyls, right? So this whole sort of sequence of new technologies has been introduced and slowly pushed out the old technologies. And the reason we're going to talk about it in the content of networks is because it's a social phenomenon, right? It is the usage of new technology by people, by some people, forces you or helps other people to start using that technology. And we're going to talk about very, very particular mechanisms that how that's happening. I want to slightly distinguish, actually I want to distinguish, significantly distinguish two different situations. One situation, one scenario is when information spreads around, and the second scenario is when we're talking about innovation. And the reason is the following. When you think about information propagation, it doesn't cost you anything to learn the information when somebody tells you things, right? You're not actually an active participant in this process in the sense, you're just being told the information, you got it, right? That the way the rumors will spread. In some way, it's also the way, viruses spread, where the virus doesn't ask you if you're okay with the virus to actually, get if you're okay with getting a flu today, right? So you're not actually part of this decision process. Versus when we're talking about innovation, this is actually a conscious process of you making decision of switching from one technology, from the older technology to newer technology, right? And that carries certain price. You pay for, carries certain price tag, because switching is can be beneficial to you, but not always, right? And you also have to pay for the switch. Imagine that you want to switch from, I don't know, again, older maybe examples, but from tape recorder to CD player, right? Which means you have to actually get rid of your old tape. I mean, all the equipment you collected, all the tapes you have collected are gone now, right? So you're paying the price for this. You're switching to new technology. Now, why would you switch to CDs? Well, the technology is better. What else?
It may be already spread in your network, for example.
And if it is spread in your network, it means you can exchange, for example. Now, imagine that you have only a tape player, right, and all your friends using CD player. What's going to happen? Right? You're out of luck because they can share among them, the new CDs, but you will not be able to get them and play because you don't have that technology yet. So, which means your social circle will actually influence your decision, right? So you do have the price you're going to pay for it, but there are some forces that actually kind of forces you to make the decision. And you, as a conscious consumer, you're kind of trying to judge this, right? You try to balance and figure out, okay, benefits versus cost, and then at some moment when benefits exceeds costs, you're going to do it, right? Again, just sort of mental, imagine a situation, half of your friends have, some of your friends have tape recorders, some of your friends have CD players. When will you switch? Like consciously in a sense that if everything, for a second, forget about that the new technology is better, just in general, when would you switch? You'd probably switch when what? How many of your friends, well, at least half of your friends switch to new technology, right? It will make sense for you to join them. Okay, makes some sense? All right, good. There are various sort of other stories I can tell you about this type of switching, and we're going to talk a little bit more about it in a few seconds. But that's sort of when we talk about diffusion of innovation, meaning switching to new technology, which meaning it's your decision you need to make to switch to it. It's not something that just comes freely to you the way rumors come, right? So we talked last time about virus propagation, information-based models or ideas, knowledge, rumors, news. Today it's about decision-based models. By the way, I'm just trying to remember, last time, what did you guys talk about in the last lecture? Epidemics. Okay. So, okay, good. Because I have two classes running in parallel, so I'm just trying to make sure I haven't missed anything. So you talked about epidemics, right? And that's viruses and infection, and information effects spreads, in a similar pattern. So today we're going to talk about decisions, and that's adoption of innovation, right? Purchasing decision. Also, say for example, joining political protest, right? Because doing that causes and carries certain risk, and that's why government wants to control social networks, right? Because this is the way you realize you judge the risk. If you see all your friends joining, you might as well join. If nobody among your friends joining, you will not. So social network acts not only as a medium for propagation of information, but it also helps you in your decision making, right? Giving you some comfort and confidence in what you're doing. And in some sense, and we're going to see this in the model, how the sort of microscopic changes meaning the decision one person makes, or the level of your sort of trust, the threshold for you to make the decision, how it can dramatically change the outcome for the entire system, right? And it's especially clearly seen on if you're talking about the protests. For example, for some people, it's enough that 10% of their friends to be in joining the protest to join. For other people, you need a threshold of 50%. But when the threshold slowly decreases and people more willingly join the protest, at one moment you get appraisal. Okay, so this is probably one of the oldest examples, and I borrowed it from one of the textbooks that's recommended for this class. It is an example of what's called its Ryan-Gross study of hybrid seed corn adoption in the United States. I mean, there have been many more studies of this type. There have been studies and this ongoing studies on the way doctors adopt and prescribe new medications. This goes back to like if you look at this, like 1924 to 1941, but it became a classical study. And so the idea is that there was a new hybrid corn introduced, and it took a while before farmers actually adopted it. And what you see on the left, actually this should work. Right, so this distribution, it shows you the propagation of information. This is every year how many more people knew about this hybrid corn, okay? So they knew, like a lot of people knew by 29 and 30s, actually by 31 probably majority knew, but only a few of them used it, right? And adoption started happening in like 33, 34, and then peaked in terms of the number of people adopting in 37. And then, by that time, it's everybody already adopted. So the point of this picture is just to show you that there is like two different separate waves. One wave is this information propagation. This is the adoption process, right? So it's sort of delayed compared to information propagation. And the way when they did the study, they found out that the major factor that has driven the adoption was not the marketing campaign, because the marketing was happening here, so everybody knew by then due to the marketing efforts. It is when their neighboring farmers were using this new corn, start planting it and telling the results. And so that's when adoption happened. So adoption happened due to really the sort of social network of farmers, right? So people trusted the results they saw, trusted their neighbors, they didn't trust the marketing campaigns. And this is actually just shows that there is this very similar, it's called S-curve, right? That you can see across different states in the United States, and it's again sort of slowly starts, then fast adoption, then it reaches plateau because everybody adopted. Now, do you know what do you call different parts of that adoption curve? There is some common names to this.
first enthusiasts.
Yeah, innovators, enthusiasts, early adopters, early majority, late majority, laggards, right? So it is the kind of traditional marketing names for different part of population, right? There's early adopters, those who actually start adoption, and then this adoption spreads among different people. And what we're going to learn about in today's lecture is how the social structure, the network, affects this adoption curve, how you actually adopt. So what influences, right? What sort of the diffusion of innovation, what actually influences the adoption? Well, first of all, there is definitely relative advantage of this innovation, right? You're going from, again, tape to CD, much higher quality. You go from CD to download. Okay, you don't need a player, CD player, and again, good quality, and you can buy by track. I mean, there are different things why you adopt, but typically, of course, it is that the new technology has some advantage, right? New corn, new seeds were producing much better, much bigger harvest than the old one. There is also a question of compatibility with the way you're currently doing things, right? Is it easy switch or hard switch? It is complexity of the new technology, right? And it can be like very, very good new technology, but if it's too complicated, people will not adopt it. If you can try, and you can see observe and see the results. So the question is, why or how new technology can take over, whether it's possible that two different technologies can coexist, or do you always get like winner takes it all, or do you have a situation when there is one technology can coexist with another one? And what stops, for example, technology from propagation? Can you give me an example, of this, for example, of several coexisting technologies? Those that are, in some sense, they're incompatible, right? But they're both good, both exist at the same time, have different market share. I'm not talking about brands, but technologies.
Like electric cars and the cars going off the gas.
Yeah, for example, these are not very compatible technologies. We know that electric cars will take over eventually, right? The way the progress happens. But they do coexist right now. You're absolutely right.
Maybe like food products, for example, brewery, different types of brewery, home brewery, which coexist with the big factory brewing, where the new more advanced technologies are used.
Like breweries, you mean like beer?
Beer.
Yeah, like beer. Oh. Yeah. You have, yes, local breweries and you have brand breweries, right? They're slightly different in terms of, the pricing, and they're different in terms of the reach, but, people prefer. For me, the most striking example is the coexistence of Apple, right, Mac, and Windows, right? The technologies are similarly level, right? They satisfy the same type of needs, but one cannot take over another. They just keep coexisting. On the phones, you get also Apple and you got Android, right? It's not brands. These are different technologies. They're incompatible, right? But they do coexist. And again, one will not take over another. If you think about brands and related to network, I guess striking examples would be mobile operators, right? You got, in Russia, you got MTS, Megaphone, and Beeline, and then what's the new one? The Tele2, right? The incoming. So they all get their 30-40% share, right? But that's about it. They're not taking, over the entire population. And there is some reasons for that, right? We're going to talk a little bit more about it. Okay. So the idea in our modeling is that we're going to look at local structure to understand sort of what's happening, right? And we're going to touch a little bit on the game theory here, right? Have you ever actually, any of you had any classes in game theory? A bit, okay. So this is going to be just a very, very, very simple story, and we're going to try to apply this the game theory a little bit here to this picture. So the idea is that here is the person, for example, and he has some neighbors. And the person gets certain benefits from using technology, right? And let's say, and there are actually more neighbors, right? He doesn't, in some sense, care what technology this guy uses because he doesn't interact with this guy, right? But he does care about what technology uses his direct neighbors. You can think about technology, or we can think about another example. This is actually a very good example with the telecom operators, right? With your mobile phones. Imagine that, that's you, and you're using. Okay, what's the most popular here? Who has MTS? Megaphone, Beeline. All right, almost 50. All right, let's say you're Megaphone user, right? And then some of your friends use MTS, some of your friends use Beeline, right? And the quality of the service of coverage, very comparable. But then there is this plan that tells you that the calls for somebody who is on the same operator, what is it? It's either cheaper or free, right? I don't know what's the current deal is. Free. It's even free. Okay, so it's free. All right. Well, let's make it cost a little bit. So and you're pretty happy, but then you realize that some of your friends switching to MTS, right? And then you have a dilemma, because you're calling some of your friends are on the same line as you are, and so you're calling them, it's free. Some other friends are on the competitor, and it costs you to call them. So, and you're kind of entertaining the idea of maybe you should switch an operator, right? Because now you can. Friends, switch friends. Okay, excellent. Actually, excellent suggestion. I haven't thought about it before, but that's definitely an option. So let's say for right now, you're kind of stuck with your friends, all right? So you cannot switch them, but you can switch mobile operator. What would be the threshold for you? If everything, sort of equal. Half of your friends? Yeah, again, think about this. Game theory is not about your emotions. It's about being reasonable, right? It is about comparing costs and benefits. If more than half of your friends are on a different operator, switching to a different operator, what's the reasonable thing for you to do? Is to switch that operator, right? Now, notice what actually happens. If that happens and you switch to the operator, for your neighbor, all of a sudden, and this, let's say, was MTS guy, and you were also MTS guy. Now, you Megaphone guy, for him, all of a sudden, he got another person in the opposite camp. So he will also he might start thinking about switching, right? And so that's sort of how this influence can propagate. And that's how this sort of game is played. All right, so a little bit more formal. It's called local interaction game. Well, it's local because it's local, right? You're not considering interaction with everybody in the world. You're only dealing with the people you communicating with your friends, with your network. And you can have different strategies, right? And strategy in this case is adopting behavior of certain type. One behavior would be staying with your operator, another behavior would be switching to a different operator. And the way it's done is there is this payoff matrix, which says, okay, so these are the options for the players, or if you wish participants, V and W. Actually, it says U here, but it is V and W. If both using one operator, you get payoff A. Well, it probably, it just costs you X amount of money. If you're using another operator, the payoff can be slightly different. For example, it can also be the same, but let's say it's different. But the critical here, if one uses one operator, another uses operator, the payoff is 0. You're not getting anything from this, right? It's in some sense that you and your friend, you're deciding using Mac or Windows, but you're actually getting usually some benefit from exchanging programs, right? Exchanging software. Well, if you both get Macs, you'll get benefit from this. If you get Windows, you get benefit from this. If one of you decides to get Mac and another Windows, well, that's it. You're not getting any benefit from the connection, right? So that's sort of this that's what this called the payoff matrix, is really about benefits, and this is like the benefits what you get, and the scientific term is that this is a strategy you take, and that's the payoff matrix of the benefit you get from the strategy. And we just actually solved this problem a second ago, just describing it. Look, this is the person who needs to make a decision. That's part of the friends, and let's say they use strategy A, right? And this uses strategy B. So the question is for this guy, what strategy he should use? Now, if if the payoffs are identical, if they're equal, right? Sort of if the value you're getting from using strategy A or strategy B is equal, for this type of picture, which strategy should this node prefer? B, right? Like if everything is equal, then of course more friends using strategy B, so it's better to switch to strategy B. But if for some reason, for example, the strategy A has a bigger payoff, right? In terms of like, better technology or something, or, lower prices, then, there's a question, right? When the threshold is. And the question is very easy to answer because when to make move from one to another situation, well, you take a payoff that you get from the strategy, you take the proportion of the neighbors, that's number of people, right? The payoff you get from this strategy is this direct, it's a payoff of the strategy times the number of people in your friend circle that uses it. And this is 1 minus p, so it's a fraction of the people that using different strategy times the payoff of that strategy. And so that's your sort of threshold, right? And if the number of people crosses the threshold, well, you're switching to different camp. That's just as simple as that. So let's see how this happens. Now, important to, and this is part of this model, we're going to look into this cascades or propagation of this new technology or strategy through the network. And here, for the modeling purposes, we'll say that there is no turning back. So it's like you switch to a new mobile operator. Within this model, you cannot switch back, right? So you were red, you became blue, you stay blue. There are more complicated models that allow you to flip-flop, but at this moment, it's just that. So imagine that we're going to look at this graph, right? This is the underlying network. And at the very beginning, let's say there are two nodes that are initial adopters. Let's say we're talking about the new technology, how it's going to propagate. Or you can think about everybody here being on, say, MTS network, and then there is guy, and this guy switched to Megaphone. Why? Well, because due to new chief of marketing at Megaphone, they decided to give away free phones and free plans for life to some people, those who want to switch, right? So, and of course, you screw friends, I'm getting new free phone and the free for life, you're going to switching, right? So these two guys, now Megaphone in the MTS land, right? So the question is, what's going to be happening on the next step? Well, look, there is this guy and there is this guy. This is a very symmetric picture, so it's very easy to reason about. So what you get for this guy, there are two of his friends are on the new network, right? And one on the old one. So if, for example, the benefits are identical, of course, the answer for this guy would be to switch, right? Now, if their benefits is different, if the payoffs are different, you can actually calculate the threshold, which is the number, the proportion of your friends who should switch to the technologies such that then you will switch. It will be beneficial for you. Does this make sense? So there is, for example, if A is equal to 3, B is equal to 2, it's a payoff. So the technology A is preferred to technology B. The threshold, you just need 2/5 of your friends to switch to this new technology such that for you it will be beneficial to switch to it. If A and B are equal, then it's going to be, for example, 2/4, so it's going to be 1/2, right? If A and B is not equal, well, it shifts the balance a little bit. But the story is exactly the same. So you need to have some of your friends to switch to new technology. And so in this case, this influence will spread very quickly. But notice, so these are two guys, right? For this guy, he has two of the new technology, one of the old technology. For him, it will make sense to switch. If you look at this guy, he has one guy with the new and two with the old. So for him, it's below the threshold, so he will not switch. Right? Now, on the next step, as we decided, these guys we're going to switch and this guy going to switch. Now they switched. What happened for this guy? Now there is two neighbors that using new technology and one that uses old. So for him, it makes sense to switch. And so step after step, the way on the first step you get these guys to switch, and on the next step you get these guys to switch, right? And so you get this wave that propagates to the network of switching, and the wave because it's step after step after step, right? And so what it's happening is like literally your neighbors changing, right? And that forces you, and forces in the sense of it's beneficial for you to also switch. So notice it's not pure. I mean, because you're looking at costs and benefits. It's not purely your decision in the sense. I mean, well, you decide switch or not, but being reasonable, the environment makes it. Forces you to make certain decision, right? Because environment changed, you have to adopt if you want to optimize your benefit. If you don't care, well, of course, stay with your old plan and your friends will enjoy free calls. Okay. Now, does it always work that way? That's quite an interesting question, because if you look at this picture, and we try to do this use the same logic, and it's very, very simple. I don't want to go through numbers here, but you can look at them. What happens literally is these are two guys, two starting points, and you can easily go through these numbers, through thresholds, and see that step after step, at first those two guys will switch to new technology because the two of their neighbors are new technology, then this guy, then this guy. So after a while, that's what's going to be happening. But what about this guy? Well, he will not, because the only influence for him is this guy with the new technology, and this two remains with the old one. The same happens here. For each of those guys, they have more with the old technology world, and so this is not going to propagate. And so that shows you that, in fact, the propagation of technology will stop. And it will stop because of natural reasons, right? Now, if you make this technology much, 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 much better, right, and that it will make so profitable to switch to it, eventually people switch, right? The barrier will be much smaller and the influence will spread. But if the technologies are comparable or close to each other, then they're going to get stuck here and will never get to here or there, right? And so that shows you that comparable technologies that on the same sort of quality level, right, that bring similar benefits within social network can coexist and not replace one another. Okay? And so mobile operators, unless somebody will drastically and dramatically change their terms and conditions or the quality of the network, will not be able to dominate and completely wipe out another technology. What's interesting is also to notice what's happening here. These are clusters, and we talked about clusters before, right? Sort of group of nodes that have more connections internally than externally, right? There's more connections internally here than here, more connections there than with these guys. So it actually tells you that clusters are those roadblocks for propagation of new technology or innovation. So tight group of people who interacts among them more than with the rest of the world, they are actually it's very difficult for innovation or technology or anything else to propagate in, because these guys are influenced by their internal community much more than by external community. And that's why, by the way, when somebody gets into some religious cult, it is extremely hard. Well, first of all, you cannot completely completely convince people to leave the cult, right, it's very hard to even pull out a single person, because when he gets sucked in, he is talking mostly his new friends who are within that cult, and he'll be listening to their opinions, not your external opinion, right, because there are few connections here, right? And so it's difficulty for technologies or for new ideas to propagate into the clusters, into a very tightly connected and coupled world. Okay, so that was like sort of, general stories of how this works. We can, in fact, build a model, mathematical model, and we actually can calculate how this process happens, right? How the spread of influence occurs. The model is the following. So we start with influence that comes from a few nodes that we select, and within the model we assume the effect only from this guy on its neighbor. So it's not a global effect; it's only a local effect. And every node will have some acceptance threshold. Again, to have a good model, for different nodes, you have to have different thresholds because we're all different, right? Again, for somebody, you need 2 of your friends to join the protest. For others, you need most of your friends. For some of you, need half of your friends to have to buy iPhones, and you will be convinced to buy iPhone. For others, it doesn't really matter what friends carry or wear or whatever. So, to have a good model, we'll have some distribution of these exception thresholds from 0 to 1. And that 1 means all your friends switched, then you're going to switch. 0 means, you don't care. You're one of those early adopters. It just, let you go and you will go. And activation, which means the node will be activated or, will switch to new technology when the fraction of your friends exceeds your threshold. All right? Again, for some people, majority of people can be 1/2, but for some people will be much more stubborn and less influenced by other people. Others, much more relying on opinion of their friends. And so we're going to start with a set of active nodes, those that are, say, got new technology, right, early adopters. And then we'll see how this process spreads and propagates through the network. It is very similar to the pictures you saw on the previous lecture when we looked into their propagation of viruses, right? But the difference there, again, virus didn't ask somebody if he wants to switch and get the virus, right? It actually just spread with certain probability. Here, there is this activation function that tells you, like, look, if less than X amount of my friends are on this new technology, right, I'm not switching. All right. So here is an example of this cascade, how it runs through the network. The first one is some empirical network. These are just some sort of randomized networks. And these are the seed nodes. And this is how the propagation happens. And you realize that depending on the network structure and depending on the seed nodes, you might either get that the new technology does not spread, or, like in this case, it actually did spread around. You can, of course, in this picture you cannot see, but the seed points are, different, are selected differently. In this case, in spite of the fact that there were like 2 clusters, you notice there are seeds here and there are seeds here. This cluster got the switch to new technology very quickly. This was much slower, but eventually both switched to new technology. Right? These are sort of some simulations done on this model. Now let's just look about this sort of formal problem, how you can formalize it. And it's really, this is an algorithm that you can really use, and, well, it's probably used by some of the companies. So the idea is the following. Like we discussed a few slides back, imagine that you're a megaphone and you want to conquer the MTS land, right? And you have some marketing budget, right, you can spend. And you decide you need to convert some of the people into. So first of all, what you can do is you can say, okay, well, I'll give everybody, I don't know, a couple hundred rubles discount, because you have fixed marketing budget, right? If you divide by the number of people, you just get very little. each person gets very little. You can do that. Most likely it's not going to work. I mean, you can give out money, people will say thank you, but not going to switch, right? Other idea would be to select individuals and give them such a discount that they just cannot resist, right? Well, give them free phones, give them free plans, give them, I don't know, whatever, ticket to Bahamas, right? You cannot do it to all of the people, but you can do it to a few. So the question is, can you actually calculate and find out those people who are influential enough on the network such that if they switch, they'll cause that type of cascade and the network will switch? All right? Very, very practical problem, right? So, people try to do this on social networks by looking to these influential bloggers, looking into the people who are mostly connected. I mean, what kind of other ideas will you have in terms of who can we give this sort of discount? Remember, we did talk about authorities, right? We can run this Hub's authorities modeling. We can calculate the guys with the highest degree centrality, who has the most number of friends, right? What else? You can look at the structure. You can look at a lot of factors, or you can just literally build a model and try to maximize this effect, right? Maximize the size of the cascade. So the idea is the following: you have an initial set of active nodes, right? So it is pretty much, let's say, with your marketing budget and your idea, you can, for example, I don't know, you can make sure that 100 people will switch. You give so much free stuff to 100 people that they will definitely switch, right? So that will be your active nodes. So the question is how to select those 100 people, right, out of all the users. To formulate this mathematically, the way to select this is the following, right? You have those 100 people. You watch for some time how this process evolves, and then you see how many people they affect, right? Then you can select some other 100 people, see how they affect. Okay. Right. Of course, you cannot do it in practice because, well, you don't have enough money to do all this, right? To do all these experiments. And second, there is just too many combinations because, imagine you have all the population and then you need to pick up 100 people, right? And then there is how many ways to do it? Well, it's factorial large number of ways, right? Because select one person is, out of million people, it's 1 million ways. Select second person is 9999. Select third person is 9998. So this is huge number. You just cannot go through this. So you need some sort of algorithm. Get the precise answers in p-hard problem, so you cannot actually compute it. But we can actually try to come up with an algorithm that does a good job. And in fact, there is an algorithm that does a good job. It's sort of influence maximization algorithm. And it's based on, well, I actually just tell you algorithm so you would understand, and then I'll explain a little bit of math, but, don't be concerned if you don't get this, the main, the math behind it. So the idea is the following. The idea of the algorithm is the following. It's so-called greedy algorithm, which means it doesn't go through all the possible combinations, but it does certain steps, guarantees that on every step of algorithm, it does the best in his situation, right? It's like in life, right? You can try to optimize your life path. I wish, well, you wish, we wish we could do it, right, knowing what's happening. But this is very hard. So what you do is on every moment of time, you're trying to take sort of locally optimal decision, what you believe is optimal at this moment, right? It might not be optimal. Later on, you look back in your life and say, why did I do that, right? But that's sort of local optimization, right? You're taking the best decision at this moment. All right, so the idea is the following. You go through all the nodes, and for each node, you start this process propagating influence from that node, simulating the propagation, and you calculate how many nodes it will affect, right? And you go through all the possible nodes. And you pick up the one that affects the most nodes in the network. You pick it up, you fix it. Now, that's your first node. Then you just take the second node. This one is you're not changing. And you're going through all the possible starting points for the second node. Like second person, you choose this one to be second person, this one to be second person, this one. And for each combination, this is fixed, you're not moving it. You're just changing the second guy. You see how both together, how much they affect. The second guy is not necessarily connected to the first guy. In fact, I mean, it might be connected, it might not be connected. Then you selected the maximum influence set from those two guys. You fix them. You pick up the third guy. You go through all the possible sort of third guys, see how all three together affect the network, et cetera, et cetera, et cetera, right? And you do it one at a time, and that's, you can actually compute. It doesn't give you the optimal combination of this, but it gives you close to optimal. There is mathematical properties that guarantees you that you're getting within like sort of 70% of optimal solution, which is actually pretty good. And so that's the algorithm, right? And that's how it works. And yeah, that's it, right? It's greedy optimization for maximum influence on the set. So it's pretty much says, yeah, pick up the first node, see how much it's going to affect, select the node that affects the maximum, and just keep going, keep iterating. And so what's interesting, this is the results. This is the results of simulation paper. Network collaboration graph, 10,000 nodes, 53,000 edges. This is published paper in 2003. And so what you see here is this target set size, and this is active set size. So what we're seeing is the following. When you select the initial set size with 5 nodes, eventually within this network, you will activate 200 people, right? So that's how many people will be influenced by you with, and again, it's a decision-making process. If you select 15, there is 600 people. You select 25, there is like 1,000 people, etc. Right? So this is optimal way to select them. Now, there are different curves here. And what's interesting is the following. So if you select, I mean, you can barely see, but if you start selecting people at random, the size of the set you're going to affect is extremely small. So pretty much if you decide, okay, here is the free phones, I just randomly give it to random people, the result will probably be close to zero, the effect, in the sense, yeah, those guys will take their phones, they will switch to your network, but that's about it. Now, if you, and again, you can barely see, but I'll trace this. If you start giving it to the nodes with high centrality or high degree centrality, so those that are very connected, this is actually quite efficient approach, and that's the line that it's right here that actually will give you the result. Now, if you try to follow the algorithm we just described, you get this top line, right? And of course, this is a small network, 10,000 nodes. Mobile operators right now have like 50 million subscribers. So the effect, the difference in between, of course, random and high degree is huge, and because high degree in this model is also pretty large. Now, the advantage of just selecting like high degree nodes is just because it's very easy to do, right? But here you can actually solve it even better and get that type of result. So that's the story I wanted to tell you about this influence optimization and influence maximization. So the key message there again, that when you have network, you can strategically position and select the nodes that will have the maximum effect on the network, right? And that effect is based on the connectivity pattern in the network, but it's not trivial in the sense, it's not like, again, it's not like with virus, where the fact that something is connected really means you're going to get virus eventually, right? Simply because you're connected. It is a decision-making process, and depending on the threshold of people, right, this influence can spread far away or will not spread. So you can first of all strategically position, right? You can affect the size, of course, by making your product much more attractive, right? You can affect the size of the influence by selecting people correctly, right? And with a small number of those seed points, you can still cover pretty large part of the network, even within this sort of decision-based model. All right? Now, question to you guys: do you now feel you understand the difference in between this, rumor, news propagation, and the decision-based models? You do. Good. All right. Now let's take a break, and we'll restart at what, 6:05, right? Or 6? What time? 6:10. At 6:10. All right. It's pretty hot here, so let's get some fresh air.
It's half an hour break.
Oh, it's
Half an hour break.
until 6:10. Yeah.
It's good.
Yeah. You don't like it?
Yeah.
I can keep you busy.
No, it's fine.
Yeah. Yeah. It's just too hot here, so I would recommend you just get outside before you fall asleep. So first of all, I want to congratulate you that you survived until the last lecture. All right. 20 out of 120 people, right, which is not bad. Survival rate. The last lecture, it's going to be a little bit less about networks, though there are going to be networks at the end. And it's not going to be very long. We won't have a homework on it, but it's really sort of interesting and somewhat politically charged topic. Do we have anybody here from sociology? We do, right?
No, I'm from social psychology.
Social psychology, okay.
Yes, more like political psychologist.
Political sciences, anybody? Nope.
I can answer for
I took some courses.
Took some courses. So who's actually survived? You guys, computer science?
Right.
No? Oh, computer science people? What else? I mean, you're from computer science?
No, computational linguistics.
Computational linguistics?
Data systems.
And you guys? Most.
Computational linguistics.
Linguistics?
Cognitive science.
Cognitive sciences? Economics?
Big data systems.
Big data systems. And I don't even know who this topic is closest, but anyway, let's see. It's actually about segregation, and though it's going to be, I'm going to be showing some new examples, particular examples. It's quite general topic, and there are a lot of applications you can think of. And this lecture is actually based. Yeah. Can I? Okay. All right.
Seminal study.
Yeah, based on the famous, study by the book, actually by Thomas Schilling, Dynamic Models of Segregation. Interestingly enough, back in the 70s, he actually could do that type of studies. Now it's going to be quite challenging in terms of his,
It's unethical.
Yeah, that's. Yeah, there is this issue, but there is, look, it's one of the things about science, right? If the phenomenon exists, you need to study it. Whether it is, you like it or you don't like it, it's happening.
Yes, but for example, as a psychologist, I have lots of ethical difficulties doing such studies nowadays. So for example, if we just look at the data, it's okay, but if I want to provide an experiment, I won't be able to do this.
Right, but you probably more refer to more like, say, like prison type of experiment, those
Yes,
things.
yes.
Now, this is not about that experiment. It's more about this model of segregation. It's really observational studies, so it's not an active experiment, right? It's not the Stanford prison story. But the idea here is it's actually quite similar to the previous lecture in the sense that we're going to be looking at every individual as an agent who are capable of making certain decisions, right, and following them through. And the idea is that an observation that Thomas Schilling made was that our cities, our countries are actually very segregated. Which means if you look at the maps of the cities, quite often people of similar race, nationality tend to live together in enclaves. And there are certain situations, that kind of enforcing that. The question is, everybody understands that this is probably not a great idea, but it's happening. And the paradox that if you talk to people, people in general are quite tolerant in terms of like having neighbors of, say, different race, different nationality, different income. So people are quite tolerant. But then as a group, you still get in a situation where cities are segregated. And so the question is, so what's actually happening, right? Are we missing something? Do people lie when they respond to questions about tolerance, or why? And so, his paper was actually quite powerful proof that there is this micro actions, sort of micro preferences, can create very significant macro behaviors. And it actually gives some sort of advice and also on how to handle those situations and how to build cities that are less segregated. And so we're going to look at this a little bit. And we're going to look about this from a mathematical point of view, try to do what's called agent-based modeling. There are certain agents, rules. So it's somewhat quite similar to the discussion on the previous lecture when we looked at the decision making, right? Because the problem is very, very similar. Let's talk about it in a second. Now, before we go for this, I want to define the segregation literally using this picture, right? So, two different colors. On the left-hand side, it's integrated pattern. On the right-hand side, it's a segregated pattern, right? So it's pretty much, this is sort of in a pure form, right, where in one case blues and greens are mixed up. In another case, they're just separated and there is a clear boundary, right? So this is the current state of the world. It's probably harder to see right now with the colors on the screen, but blue corresponds to white people. There is Asian people. The purple, I think, yes, there is the Asian. Then there is black and Latinos, right? And if you look at the different, and this is U.S. today, right? And if you notice, there is significant. You don't see here colors sort of mixed up. What you see is the regions where different nationalities, races prefer to live, right? This is Chicago. Here is Miami. There's, of course, huge Cuban population there, Latinos. You think about Seattle, there is this huge Asian in the center. New York, well, Manhattan is predominantly, white. LA, there's the central LA, which is black. Then if you look at the, Highway 1 here, there are mostly white. They're then here's Latinos, etc. So it is very, very segregated the way it is. Now, if you actually, we don't have this type of map for Moscow, but if you live here long enough, you realize that there's some parts of town which is quite different in terms of people who live there from other parts of town, right? And so the question is, aside from even sort of economic availability for the places, why is this happening, right? And the question is from this sort of dynamic, and preference point of view. This is also another picture which is sort of the consequence of the segregation. This is Bay Area, San Francisco. Here is like Palo Alto, and that's where Facebook and Google, and this is San Francisco, and this is Bay Area high school graduates, right? So those people who actually graduated from high school, right? Even finished high school. And of course, this is it's a rich white population. There is a quite strong here Latinos population. And again, you notice that there is a correlation, very strong, of course, correlation between income, the race, and the graduates from schools. So, and again, you don't see them scattered across, right, the regions. This is old news now, right? This is 2012 presidential campaign, but you can actually get the same map for the latest U.S. presidential campaign. Again, you don't, the red and the blue is those who voted for Obama and those who voted for Republicans for Mitt Romney back in the previous election. And again, notice that it's not like there's single sort of blue squares among Red Sea or single red squares among Blue Sea. There were sort of enclaves, there were regions of blue, right? Regions of blue, regions of blue, regions of blue, and then there is, regions of red. So they're quite, continuous, right? So of course, political preferences follow, a lot of things, but you notice that even by looking by the political preferences, country is quite segregated. Yeah, you wanted to say something.
Yes, it's especially like the factor of the center, because you can see, for example, some of these regions are with low income, and for example, the bluer the regions, the higher actually is general income, and so on. It's like if you combine it with other such maps,
It is
interesting thing,
It is about income, but not only, right?
Yeah.
Because, for example, here there is not such high income. This is not such high income. There's high income in in New York. There was high income, of course, California. This is not a high income state.
Yeah.
This is not high income. This is Latinos. So yeah, of course, there is for each and every region you can come up and explain why. And maybe here it's like because Obama campaigned a lot, right? And he is. And the black voters showed up a lot. So
that the center is like predominantly Republican.
Predominantly
Almost,
Republican,
yes.
historically Republican,
Historically
yes.
Republican,
Yes.
predominantly Republican. Almost every election is like
Yeah,
this.
yeah. No, but what I'm saying is, it doesn't matter what the original reasons are, but what we see is there is a quite clear segregation, right? And you don't see the people from, you don't see the sort of uniform mixing of different people, right? Of different voters. So you can observe, segregation in all kind of forms and results, in even here in the voting patterns, right? So what we're going to try to do is we're going to try to model this, right? And we're going to follow very, very simple model that was proposed by Schilling back in 1971, and then we'll just, at the end, we'll add a bit of network analysis to it. So we're going to think of population consisting of two types of agents. Agents of type A and agents type of B, right? And let's think about just very, very simple, for a second, very, very simple geometrical model where, think about like Russian's dacha, right? You have the house, right, and then you have neighbors around it, right? You can have like 4 neighbors or 8 neighbors, doesn't matter, but it's like almost like a checkerboard, right? So you have your neighbors. You also have something different from Russian's dachas, where you have some of those are populated, some cells contain agents, and others just empty. So they're available, so you can move there. And then here is a sort of the centerpiece. Is that the decision-making story? Every agent, every person, right? Every agent in this game, in this process, wants to have at least some fraction of his or her neighbors of the same type. Again, you can think about income, you can think about race, you can think about whatever, the same type, right? Gender, I don't know. Whatever. Well, this is all politically charged, right? So it doesn't matter what I say. I'm going to be politically incorrect in one of those statements. But there you go, right? That's why it's very hard to do those things today. But anyway, so every agent wants to have at least some fraction of his type, right, surrounding him. And people are quite tolerant. Means, like I'm okay with 50% of people not like me living, around me, right? I'll be completely intolerant if I say like, no, I want all 100% of my neighbors to be just like me, right? Or I can be completely tolerant and say, I don't care, right? Whoever lives, which is, also a good thing, right? And there is this distribution of people preferences, right? So that's what we're going to put within this model, this distribution. And here is the way the game works. There is some starting positions, right? And then we let, on every step, people to, if they're not happy, and when you live in the situation that you're happy with, and let's say I want, 60% of my neighbors be of my type, right? I just stay there. But if I'm not happy, I can move to any of the empty locations that will satisfy my constraints. Okay? So, what happens is you look at this checkerboard, right? Some empty cells, some occupied cells, different A and B people, and then they start moving. So they moved, right? So the step one, they moved. Then what happened? Even for those people who did not move, some of the neighbors might change. And maybe they were in a position where they were satisfied, but now there are people of different type moved in their neighborhood. And all of a sudden, the number of the proportion of the people who are of different type exceeds their threshold, the threshold of comfort. Right? So on the next iteration, what do the people do? They move. Now, of course, in order for them to move, there should be other empty locations where they can move and they will be satisfied, right? But if those occasions exist, they move, right? That again changes the balance. And so we just keep happening and happening and happening until the system finally gets to the point where either everybody is happy and satisfied, or there is just no place to move, right? Because every location you get to, there will be something wrong with it, right? Your preferences will not be satisfied. And then you're just not moving. You're like unhappy dweller, right? You're sitting there, but you cannot move, right? So quite unhappy society. So the question is, clearly that within this game, everything depends on, well, first sort of structure, right? Location where people live. And second, individual preferences, right? If you have everybody who is insanely happy, who doesn't care at all, right? Nobody will move ever. If you have people who are extremely concerned about their surrounding, right? And they want to have everybody of their type, what's going to happen? Most likely there will be no movements either because it's very hard to find those type of locations, right? There will not be. It's just one situation, everybody will be happier, right? The other situation, everybody's unhappy but cannot move simply because their requirements are too high, right? They will not find that type of place. And then there is a scenario in between. And so you'd expect that if people are tolerant, what do you expect to see? If if I'm like 50%, I'm okay with having 50% of different type living next to my door. And you would expect, okay, well, this will be somewhat mixed, right? But that's not what the model shows, and that's probably the most sort of surprising result of this model, right? That even with tolerant people, you get a very, very segregated society. Which is quite strange, but if you see how model evolves, you'll realize why this is happening. Okay, so again, like I'm kind of referring to the previous lecture because it's quite similar in the sense of the sort of the logic, right? You look at the neighbors, and let's say we're looking at this agent X, right, which is in the center, and the white cell is the empty cell, and then there's the two types. And there is a preference threshold 3/7, which means if more than 3 of 7 people, of his type, he is happy, right? If less, he is not. So in the situation on the left, the central agent so he got 1, 2, 3 out of 7 neighbors of his type, so he's pretty happy, right? On the right, has only 2 out of 7 of his type. He's an unhappy agent. And so that means this guy, on the next step, on the next iteration of the game, he will try to move somewhere. Now, it's there are different sort of models. If you're going to move to its nearest location, tries to move here or tries to move somewhere else, it's the rules of the game. Now, will he move here? Yeah, if he does have any more neighbors, he will not because there's no of his type people right around, and so he wants to have some of his type of people surrounding him. But if thinking that there is more people living there, maybe that location would work if there are more of red guys, here below this line. But that's sort of the game. Make sense? Okay. This is actual screenshot from the paper that Thomas Schilling did in 1971. This was his starting location, and empty spots are empty spots, and there's this 2 types of agents. And then he played this game, right? He actually played this game with pen and pencil, like literally drawing this. That's not a computer simulation. But after several iterations, right, bunch of iterations, this is the result he got. So even with threshold around 50%, which means people are quite tolerant, he got very, very, very strong segregation. So people were pretty happy with, if you have half of their neighbors of a different type. But the dynamics of the entire system eventually led to this. And the reason that happened is because you were pretty happy, but then one of your neighbors who is unhappy moving, right? Then all of a sudden, your condition is not satisfied, and you start moving in the same direction because other places will not satisfy your conditions, right? And so then you get this segregation picture.
This is the final step.
This is the final result, yes. Pretty much after that, yes, there is no reason for anybody else to move. I mean, again, this is like sort of simulation in his paper. If you're interested, take a look. So here's a bunch of simulations done, of course, recently. And I mean, this is a very popular model. What you're going to see, what you see here is on the left, this is sort of initial state. This sort of the salt, the white spots, that's like empty locations. And there are 2 types, green and blue. Vacancy 5%, so there's like 5% of empty locations, right? And the tolerance is 50%. And this is simulations. After 10 steps, after 100 steps, after 400 steps. So it's actually led to complete segregation.
And what if we start with partial segregation? Will it become segregated too?
Yeah. So it all, the solution converges to here. So you can start from here, you get here. Okay. Now, there is no sort of mathematical equations that describe precisely like differential equations like we looked into when we talked about virus propagation. You talked about viruses, right? There is differential equations that describe it. There is no differential equations. One of the reasons is because there is this, it's differential equations. You use them when there is a sort of, the probabilities or whatever you describe is smooth, right? You can differentiate functions. Here you have a threshold, right? And this model or the model that we looked into in the previous lecture, both of them have this threshold behavior. You don't do anything unless the percentile of your neighbors, switch to MTS, right? And then you do something. And the same is here, right? You just count how many of your neighbors, and then you're either satisfied or not satisfied. So it's sort of binary decision, 0 or 1. And that's when differential equations do not do a good job. So here is different examples, again from the same paper. These are different vacancy patterns, right? Different vacancy patterns. And this is, again, time interval. So what's happening? Okay, so model by itself. The model is extremely simple, and you can actually write that model yourself, and you can simulate it. You can easily write it in R. Well, actually, in R, you can probably just Google and download a model for Schilling. Well, there are like tons of those models available, even like demos, where you can just download the model. Or you can write your own. So the model says, if we have n nodes, and then there is sigma is a fraction of occupied nodes, right? There is n nodes in the system. That's a fraction of occupied nodes. So the obviously the number of nodes of type A and number of nodes of type B should be equal to the total number of occupied nodes, right? Occupied sites in the system. And then you can calculate the proportion of unlike nearest neighbors, right? So you calculate the proportion of the people who are not like you around you, right? And that's just, it's going to be number of people divided by the total number of people. And then you have a utility function. Again, this sort of preference functions that is equal to 1, which is you're happy, is a fraction of unlike nearest neighbors is below a threshold, and equal to 0 if it is above threshold, right? And so what you want is you want to maximize, every person wants to maximize this, right? Maximizing this, again, it's a binary function. You're either happy or not. So you're maximizing happiness. You're very, you're a very easy person, right? It's just you're happy or not. There is no level of happiness. But it's 1 if you're satisfied, it's 0 if you're not satisfied. And in this model, you can also measure happiness of the population, right? By just counting how many people are happy, or just adding up those numbers. Because if you're not happy at 0, if you're happy with 1, well, the total sum will give you the level of happiness of the entire population. And you can think about various sort of geometric layout. You can think about this layout, right, when you have, I can call it dacha layout, right, this neighbors, right? And you can model this as a network if you wish. Here's a node and here is the neighbors, right? Now, and that's where it is very easy later on to switch from this classic thing that Schilling did, right? Switch it more onto the network type of situation, right? Where it's not necessarily geometrically neighbors, but it's in general could be people you're communicating with, right? You can instantly think about, and those, well, those who work in sociology might even notice, and this phenomenon exists, but at least in Russia, I'm not sure if it's so obvious, but if you go work for some multinational companies, say in US, you would notice that there are some enclaves within the company of, say, say Indian guys who will tend to group together and they will take over some divisions of the company, and most of them will be transferring there, and then there will be maybe Chinese group within the company, and you'll realize that they report to the same people, and they created their own trees, and then there is this and this and this. By the way, Russians are mixing really well. They don't create enclaves, but and so it is not necessarily geometric effect, right? It's not necessarily the fact that we have neighbors left and right. It's also a social phenomenon in terms of who you interact with and where you feel comfortable. Let's say all your colleagues. You work with the colleagues that not like you. So the question is, and you can even think about physicists working with sociologists, right? How comfortable you will be in this surrounding. I mean, maybe you would prefer to be among physicists, right? And so it's just sort of different types and how people react on that, right? It's a comfort level. It's sort of the acceptance threshold. Okay, so what does a model do? It's an algorithm. We take time steps, 1 to t. At every time step, we randomly select an agent, right? Pick up a person and compute his utility. Well, utility means happy or not, right? And if his utility is 0, which means he's unhappy in that location, we move to empty location that maximizes utility. Well, maximize meaning you're not moving to just empty location that keeps your utility 0, but you move to a location that raises your utility. And you can have randomly pick up a location, or you can, for example, go for a nearest available location that satisfies, it doesn't matter, it's just different rules. And you just keep repeating this process until the utility either maximized, which means everybody is happy, we're living in a happy world, or we got to this frozen state where just there's no place to move, right? So utility is less than it is possible because half of the people happy, half are unhappy. But those who are unhappy, they just cannot move. There's just no place to move. And then we can calculate the total happiness of the society, utility of the society. And we can also calculate different, now in order for us to understand how a model operates, we can calculate different mixing indices. So mixing is how things are mixed up, right? Remember I showed you the very first picture, there are two situations, right? On one hand side there was sort of the greens were with blues, on the other hand, on the other side it was separated. And there are different indexes that helps you to calculate this, right? That just sort of gives you a number, right, of how separated things are. Like, for example, a proportion of ties between groups. If the proportion of the ties between groups is small, then this segregation index is equal to 1, which means it's fully segregated. So this is a number of ties between groups, right? So if there is green and blue and they're mixed up, then there's a lot of connections among them, then this is a large number, then segregation index is small. Even on the opposite, you have only boundary, the number of ties is very small, because it's only the boundary nodes that connect different groups, then the segregation index is high. And there is the same kind of story here. Remember, this is the index that it's equal to 1 if you're satisfied and 0 if not satisfied. It also gives you the same kind of thing. So now to networks, right? I promise that by the end we'll look at the networks. These are different network types, and they're this is a regular network, right? So we have regular. This is pretty much the Schilling's sort of initial modeling, and then there is a random network. Then there is a scale-free network, and there is called fractal network, and these are like on a different level of different level of intensity of the connections. But this is the same sort of type of networks. And when you run those type of simulations, where do you think you're going to see bigger segregation patterns or less segregation patterns? Actually, I don't know the answer, so I mean, we'll see the answer in the next picture, but you think this one has the least segregation?
Yeah, I guess.
Okay. Well, we're going to see. We're going to see. And do we see it? Yes. Can you guys see colors a little bit? Okay. So this is the results. Oops. This is the results of the simulation. So this is a regular graph, and you got your segregation, right? It's a little less here on this network, the network that is random. So regular got strong segregation, right? You pretty much got this. This one also got pretty strong and clear segregation pattern, right? And in fact, this is more of a picture if you think about like organizational structure in a company. That's what it is usually, right? And this one, it's actually not that bad, right, compared to things. And there's some parameters here, right? The one that just this is the threshold parameter and the filling factor. And so here is the sort of the striking summary on the spatial segregation. So first of all, there is this different type of networks, right? Grid, random, scale-free, and this is fractal network. And you notice, yes, they're slightly different, but they show the same type of a pattern, which is where you have this tolerance, right? It's how tolerant people are, right? And this is how mixity, which is opposite to segregation, how strong it is. And notice what happens. If tolerance is very, very, very low, and you start with a mixed state, what happens? Nothing happens, right? They can actually, because they don't have place to move, right? And so the mixity remains high, but what's important here, and this is not shown here, but the happiness of a population is very low, right? Now, you can get on the very different type of when the tolerance is 100%, then nobody moves because, everybody's happy. It's all mixed up, everybody's happy, happy population, nobody moves. But what's amazing is these numbers. When you have 50%, right? It's just 50%, which means you're very happy with having half of people of a different type being your neighbors. There is a segregation happens. The mixity drops dramatically, right? And that is, that was this extremely surprising factor in the model, and that's why the model became very, very well known, is because, in fact, of the individual preferences, the collective behavior is extremely different. And so that's probably the key message here, that in spite of your individual preferences, the behavior as a group, those individual preferences, these micro-motives, can drive huge changes, can create huge changes in macro behavior. So the change from your tolerance level from 30 to 40 can drop dramatically the mixing.
But I think it was like when we have 30, 40, 60%, it shows, it creates some like polarization in their opinions. That's why, for example, they become active groups, they become more organized, and that's why they don't mix so well. They are kind of strange. Because that's like what I see as an explanation why it drops.
Could be. But the thing is, you're kind of referring to the social events where people can start organizing. But notice that we got these results in the model, in the agent-based model, where they don't socialize, they don't, we didn't put grouping as a factor in this model, so there should be something else.
Still it's more, but still there is identification, because like they see that I need someone around me that identify as or I do not. So it's still a group process, because like as psychologically speaking, it's identification is as itself is a group process, because it connects you to the group. It's a sense of belongings. That's why, for example, I see that at 40, 50, and 60, there is more likeliness that there are two separated groups, at least in the mindset. Good.
All right. So that's sort of the, that's a summary. I mean, little said lecture, but the result is that spatial segregation is taking place even though no individual is actively seeking this, right? But as a group dynamics, it leads to a segregation. And network structure does affect it, right? And depending how you set up your environment, it can either enhance it or reduce it. For example, as you can guess, if you put a freeway that splits city into two parts, what happens? Obviously, it enforces segregation, right? Even here, if you think about this, the Leningradsky Prospect, right? It forces segregation. There are different groups of people living on different sides of it because there's no easy crossing, right? Or think about the third ring, Begavai, it's also very different population lives on different sides. So there are things that enforces, kind of helps segregation. There are things that, literally geometric things that can prevent this from segregation or help to reduce it. And then it's just really, this is literally the results from the paper, right? The summary of the paper, that's certain fixed characteristics like, race, income can become correlated with things like location, right? So certain type of people will live in certain locations. Right? So that's the famous paper. This is a summary and sort of the mapping it onto networks. And pretty much you notice that the last couple lectures we talked more about sort of this agent-based modeling, right? And there are a lot of phenomena, especially in social sciences, that is very, very hard to describe with equations. So what you do when you cannot describe it with equations, you start simulations, right? You start building models where you take those agents and you assign, give certain rules, and based on those rules, those agents act, and then you, look up observe results. Any questions about this? Okay.
Are there another examples of simulation, like Worm's perspective, political science, and so on? Because it is more like it's more like about data science, but not so much applicable to theoretical mindset. That's why I'm asking.
So you want me to give you more examples, or you have more examples?
No. I want to see more examples. Yeah.
So I don't have more examples. Again, I'm coming from more of data science world, right? But I encourage you to Google, right? If you just type in model of segregation, and then you type in sociology or whatever you're interested in, you will get tons and tons and tons of papers, right, on this. Okay, so we are in that wonderful moment when we're all done. Now, let's go and briefly, we have 10 more minutes at least. Let's check on what you do remember. Because remember, there's going to be a test, right, at the end of the course. Yeah, there's going to be a test. So it's not today, but it's going to be. So introduction to network science. Okay, fine, whatever. Descriptive network analysis. What was that about?
It was about the plotting the graph, showing the vertices and the distributions.
Oh, this is nice. Somebody remembers power law. All right. So yeah. So this is degree. So we looked at the network, and we look at the network as a whole, right? As a sort of group of nodes, and we looked at statistical properties of the networks, right? We looked at the node degrees and degree distribution in the network. We looked at I think it looked at small world, right? The fact that most of the networks that we deal with are small world networks, which means like 6 degrees of separation, form the world. And also we talked about clustering coefficient, right? The fact that in social networks there are very many triads or triangles, right? So a lot of sort of social interaction forces people to form these triangles. And so in social networks you have small world property, you have those triangles, and you do have power law distribution, which means there are some people get it all and others are like poor guys out there with very few connections, and celebrities. Okay, mathematical models of networks. What was that about? 3 models. Random graph. Barbasha-Albert. And? Small world, and the guy's name? No, Rene, that's random graph. That's that R-Rene. Watts and Strogatz, right? Okay. All right. So random graph, what was that about?
The edge is added as a graph with some probability.
Yeah. So you go through all the possible nodes, and they are connected with certain probability, right? So that's completely a random story. Then there is this model which is Barbasha-Albert, which was power law they created. So the random graph didn't have this power law property.
We give to the model some number, and every time we add a new node, it has this connect. We give to this node connections, and
No. Okay, you're right. So look, the right thinking, right? In the Barbasha-Albert model, it is the rich gets richer phenomenon, right? It is the fact when you get new node coming into it. So first of all, it's dynamic graph, right? So it's growing with time, and then when the new node comes in, it comes with a possibility to connect to with few edges. Can connect to other nodes, and it connects by what's called preferential attachment. So it prefers to connect to the nodes that already have a lot of connections, right? So that's why rich gets richer. So it's preferential attachment model. That's Barbasha-Albert. And the last one, Watts and Strogatz, what was that?
Regular graph in which we replace edges, so it's circular looking, and in which we replace edges with edges which shorten those passes.
Right. Yeah. So I mean, it happens to be circular simply because that was a picture, but it doesn't matter if it's a circular graph or whatever. But the point is, you take some regular graph that has very strong clustering, so it has those properties that you have strong local connections, and you add long-range connections. Right? You either replace some of this nearest neighbor's connection with long-range connections, or you just add them. And then in your network, you simultaneously will get clustering, so like local connectivity, and also global connectivity due to this long-range edges. Right? Okay, so those three models. Number 4, node centrality and ranking. What was that about?
Centralities and ranking.
What centralities do you know?
Degree, betweenness, closeness, eigenvectors,
We never talked about alpha centrality.
We don't review this.
Oh, you did? Okay. Power law, I'm sorry, power. Page rank, and then Hobbes' authorities. So the degree centrality, well, obviously, right? It's a node degree. Between the centrality, what's it about? Number of shortest paths that go through the node. Closeness centrality.
It should be the sum of the distance of the nodes. Like we calculate all the shortest path to every node, and then we get.
Yeah. So it's inverse sum of the distances. So in some sense, it's the most geometrically centered. So the sum of the shortest path from that one to everybody else will be the smallest, right? That's the most central. And the idea was eigenvector centrality. What's the idea there? Yeah, that's eigenvector. Okay, so yeah, so you have the adjacency matrix, and then you find eigenvector over that matrix. But sort of intuitively, the idea is that when you have a node with certain centrality, right, it's not only the number of neighbors that affect that centrality, but it's also the centrality of those nodes. So if you're connected to nodes with a high centrality, your centrality will be higher. So the centrality of the node is determined by the centralities of his or her friends. And that mathematically transfers into eigenvalue and eigenvector problem. Right, then we have this page rank story. What's page rank?
We take the graph and some random paths in this graph. If the graph in some time of the process, time process, the graph moves from one node to another randomly because it should behavior like a human.
Okay. Yeah, so it's a random walk model, right, where you where you can hop from the node to another node, right? And if you do it for a long, long time, there'll be certain probability you end up on different nodes, and then you rank by that probability, right? And so pretty much it means you have a lot of paths that leading through the node. It will have high page rank. And then there are Hobbes' authorities. Last one. Do you remember that? But the idea is that you have, every node can have like two flavors, right? Two metrics, Hobbes and authorities. And, you have high Hobbes degree if you point to a lot of high authorities, and high authority degree if a lot of Hobbes with high degree points to you. But in some sense, Hobbes, again, is those that points to things, and authorities those where other nodes point to. And it's also becoming an eigenvector eigenvalue problem. All right, communities. What's that?
It's just some subgraphs which have higher inner edge densities than outer.
So it's subgraphs, right? It's a group of nodes that are tightly connected among themselves than with the rest of the graph. And we can look at the density, internal density of the edges, so comparing the density within that group compared to average density. We can also look at the metric which is called modularity, right? That actually tells you how many connections you have with respect compared to how many would be there if it was a random graph, and so there wouldn't be patterns. And that's sort of we used we used algorithms to find that separation. We talked about two different types of communities. One was non-overlapping communities, right, where the node can belong only to one community, and then you can actually cut the edges, right, and separate them. And then there is also the notion of overlapping community, where there is, node can belong to two communities. For the second one, we didn't talk about the algorithm that allows us to detect it. Yes?
What's the difference between communities and clusters?
Actually, no difference, right? People call it, communities. People call it clustering. People call it grouping. There is one important thing is that there is a name collision because there is this clustering coefficient, which has nothing to do with the clustering, right? It's just a measure of number of triangles in the graph, right? So unfortunately, that's the names that exist right now. Sometimes clustering coefficient is also called transitivity, so then it's, you're not mixing it. But clusters or communities within, if you talk about clusters within graphs and networks and communities, that's the same thing. Okay? It's just different notations, the same way as people talk vertices versus nodes, edges versus links, it's all the same. It's just because it's coming from different sort of fields of science. Make sense? Okay. Yeah, don't mix clustering coefficient because that's about just triangles versus clusters among nodes. And so we have those communities and the algorithm that allows you to detect them. Epidemics, what did you learn about that? How many models are out there?
It depends on the number of states.
Yeah, but I mean, there was like models, like very, very fundamental types of models. SI, SIR, SIS. So do you remember the difference?
Depending on the number of states and the transition between the states.
And the transitions, right? So SI models, there is susceptible that can be infected, right? And that's it. Nothing else happens. And if you have that type of situation and you're on the network, eventually every connected component will get infected because there is no sort of way out, right? It spreads. Then there is SIS model, which is susceptible, infected, and then recovers. Yeah, and then back. Susceptible, infected, and then susceptible again. So people recover. It's like sort of flu kind of thing, right? And then they can be infected again. And in those situations, depending on the one very important ratio, you either get the situation when you get, all the graph will get sort of sick, right? Or you will get sort of percentage of the nodes that are sick. They might change, so it will be different people who get sick, but the ratio, let's say 30% of population or 20 will preserve, but it will going to be different people. So it's like sort of rotating sickness, right? In some sense. Now, do you remember what's the important ratio?
Rehabilitation rate of illness rate.
Yeah, so it's a ratio of the rate with which recovery happened versus the rate with which infection happens, right? And if this rate is, if the ratio is, what's the boundary? It's trivial, right? No. What I mean, the rate, if the recovery rate is equal to infection rate, you have you're in the sort of boundary state. But if recovery rate is higher than infection rate, then what happens? The infection goes away, right? Because you recover faster than the infection propagates, and other way around, right? Okay, and then there was the last model, which was SIR, right? Which is susceptible, infected.
Recovered and no more infected.
Yeah, well, recovered is, I would say, removed, right? So it could be either, it could be recovered in the sense that he cannot be susceptible, is not susceptible anymore. Like think about like some strong disease, you get immunity, you get immune after that, or it's removed, meaning died, removed from population. So, and that model also has this sort of threshold. And now, if you think about the classical models where it's about the entire population, where the mixing, which is interaction, can happen across the entire population, it's a very simple ratio of recovery and infection rate that gives you this sort of threshold from having an epidemics and not having epidemics. When you have a network, there is also first eigenvalue that is in there, right? You compare not to one, but to the first eigenvalue. And so it tells you that the structure of the network obviously affects the spread of the disease. And it just, again, if you think about the small world network or, say, regular grid network, where infection would spread faster? Small world. Why? Well, because there is long-range connections, right? So it will actually make infection go fast and spread around. And that's sort of what we're shown, I guess, in some of the papers. Okay. Well, and now the most interesting. Let's see what you remember from the previous hour. Diffusion of innovation, what was that about? How is it different from epidemics?
It's different from epidemics because we have active agents who are motivated to spread the idea. When in case of epidemics, it happens simultaneously. Impact from these agents.
So the key is, with diffusion of innovation, the key is that the decision-making at threshold, right? So when we looked at an infection, the agent itself who get infected didn't make any decision about it, right? He was just unlucky one who is in contact with somebody who is already infected, and so there is a probability that infection spreads to him. Here, you kind of look around and you decide, okay, I have 5 of my friends sick, do I want to get sicker? Well, kidding. You have some of your friends switching to technology. You look at the benefits, you do cost-benefit analysis, and then if it makes sense to you, you switch, right? So this is the key there for the innovation properties, and the connection between that and clustering, again, that in network communities, that innovation have very hard time to propagate into the communities, into clusters, because the way things are connected, and so within the cluster, people are influenced by the people within this cluster. And so innovation, new ideas, new technologies have a hard time getting into the clusters. And the last one, spatial model of segregation, what the key message there?
Everything has to be segregated. Everything tend to be segregated.
Yeah, be tolerant. I mean, otherwise, even if you're 50-50, it's going to screw us up. Okay, done. We're done with the course. Any questions, concerns, complaints? Опросник? Oh, sample questions, you mean?
Yes,
Yeah.
Maybe sample tests.
Sample tests. Let me talk to Leonid. I think we can probably arrange some of the sample questions. It's not going to be a lot, but some of those from previous years.
Because they said that, for example, that we will have to solve problems, so we at least need to an idea
Yeah. So the problems can be for example, I don't remember exactly right now. So what's what we had in the test in the previous years, but the level of difficulty could be, okay, here is your small network of, I don't know, 4 nodes, 5 nodes, thinking about this diffusion of innovation. Here is the threshold for the nodes. Let's say it's 1/2. Here's the 2 nodes who are, who are getting freebies and they're switching technology. Calculate how far this innovation would go on this network. Right? So you just literally need to do this analysis we did in class, looking at the neighbors. I'm not sure if you have, and of course there might be questions, I'm sure there'll be questions on this centrality, right? Here's your nodes, here's the graph, find out the nodes with the highest, degree centrality. We probably will not, yeah, between this is harder, or eigenvalue is harder, but, so the questions would be manageable. So we're not assuming you're doing a lot of math on this test. It's more about conceptual understanding of these topics. All right. Okay. That's it. Thank you. We're done.